Good afternoon, everyone. I hope I'm audible to you guys. Uh, welcome to the week 4 problem solving session for the course Fundamentals of Food Process Engineering. In this week, we'll be solving problems related to week 4 syllabus that includes the process of evaporation and the, the evaporator operations. All the evaporation process that happen in the evaporator, we'll be solving some numericals as well as some theory based questions. During the class, if you guys have any doubts, please either unmute yourself or post it in the in-call messages so that we can clarify those doubts. If you guys have any if you guys can find out the answer also, you can post your answers in the in-call messages. Okay. So moving on to question 1, we'll be discussing both numericals and theory based questions. And if you guys want me to repeat any part, please let me know. Liquid food containing 13% total solids is concentrated to 38% solids in an evaporator. If the mass flow rate of the feed is 120 kg per hour, calculate the amount of water evaporated in the process. Before we proceed with the problem, can anybody tell me what are the inlet and outlet feeds in an evaporator? When you have an evaporator system, you will have an inlet stream and an outlet stream. So, what are the streams that go inside the evaporator and what are the streams that go outside? If you know the answer, you can just post it as a message or you can unmute yourself and answer the question. Okay, if this is a diagram of an evaporator, and as you can see here, there are multiple streams that are going inside the evaporator and some streams that are coming out. So when you look at the inlet stream, you have two inlets here. One is the steam, the form of one is the inlet steam that is used to heat your feed. The second stream that goes inside the evaporator is the feed that contains these solids that is mentioned in the question. So you have a feed coming in and steam coming in. The steam will heat up the feed to a certain temperature, which is generally the boiling point of the feed. And once the boiling feed reaches the boiling point, you will have two streams going out. One is the vapor due to the boiling. The other one, after the vapor has been separated, you will have a concentrated product. That is, all the water vapor would have evaporated and you will have the concentrated product here. So you will have a product also as an outlet. So the feed will be converted, will be boiled and you will have a vapor stream and a product stream. And the steam that is used to heat up the feed will then condense to form uh, liquid stream, which is almost at the same temperature. So you will only have the phase change that is happening. You generally will not have a temperature change when it comes to your steam inlet. So the temperature of both the inlet and outlet will be the same. It is just that the phase change will happen due to the transfer of heat. I hope this is clear. What are the inlet streams and what are the outlet streams? So you have two inlets, feed and the steam. You have three outlets. One is the condensed steam, the product and the vapor. So we'll move on to the question and figure out how to solve it. We have given here that the XF, that is the fraction of the solids in the feed stream, is given as 13%, which is 0.13. And we know that the after evaporation it is concentrated to 38% solids, which means that the product stream has a fraction of total solids, that is XP, as 0.38. Okay, so let's say F is the mass flow rate of the feed, V is the mass flow rate of the vapor stream, L is the mass flow rate of the product stream. XF is the fraction of total solids in the feed stream. Xp is the fraction of total solids in the product stream. So we have been given that the mass flow rate of the feed, which is F here, is equal to 120 kg per hour. We have to calculate the amount of water evaporated in the process, which basically means we need to calculate V, because water evaporated is collected in the form of vapor here. So we need to calculate what is V. Can anybody tell me how to proceed with this? What is the first step here? Okay, generally when you have when you do evaporator based problems, we start with a simple mass balance. So you can do a mass balance on two different stuff. First, you can do a total mass balance where you balance the mass of the entire feed that is coming in and going out, entire streams that are coming in and going out. So the total mass balance is equal to F equal to L plus V. We are not including steam here because it's a separate coil itself. There is no mixture of the feed and the steam. You are not mixing the feed. There is no direct contact of the feed and the steam. And whatever steam you are letting in, you are going out, taking it out as well. So you are not including steam in the total mass balance. We are including all the other streams that come inside and go outside of the evaporator. Hope this is clear. The steam and the feed are not in contact, first thing. Second thing, or more importantly, since they are not in contact, whatever steam you are sending in, you are taking it out. So steam is not included in the total mass balance equation. We include only the streams that correspond to your liquid food. So inlet is equal to outlet. That is what we have done here. Inlet, which is F, is equal to outlet, which is L plus V. This is your total mass balance equation. So this is one of the equation that you can do. The second equation is you do a mass balance only for the total solids that are present. So if the mass of the total solids remains constant also. So F into XF, which include XF is the fraction of total solids and F is the total amount of feed that you are sending in. So F into XF will give me the total amount of solids present in the feed stream. So that is the input equal to output. So that is equal to L into XP. This will give me the total amount of solids present in the product stream. There is no such thing as XV here because only water vapor is being evaporated. Solids do not evaporate. So whatever solids you have will come through the product stream only. This will only have water vapor. So even if you have something known as V into XV, your XV will always be equal to 0. Is this part clear? Is there any doubts in these mass balance equations? Because we will be continuously using it throughout each and every problem. So we have a total mass balance and we have mass balance for solids. With these two equations and with the given numerical values, we can solve for what is the V that is asked in the question. Substituting the values in this equation, we have 120 kg per hour into XF, which is 0.13. L we do not know, so we keep it as it is, and XP is given as 0.38. From this, we can calculate L to be 41.05 kg per hour. This L, we already know what is F, we calculated L, so we can substitute back in the total mass balance equation to calculate what is V. So substituting back in the total mass balance equation, 120 equal to 41.05 plus V. So V is equal to 78.95 kg per hour. The answer given here is option C. Is there any doubt so far? Any of the doubts in the mass balance equation? Do you want me to go slower? We can go a bit more slower as well. If there is no doubt, we'll proceed to the next question. Okay then, moving on to the next question. In a single effect evaporator, 132 kg per hour of apple juice is entering uh, at a boiling point temperature of 15 degrees Celsius, 50 degrees Celsius is concentrated from 8% to 26%. Saturated steam is entering the evaporator at 375 Kelvin. The latent heat of vaporization of the steam at 375 Kelvin is 2150 kilojoule per kg, and the specific enthalpy of the saturated vapor at 323 is 2250 kilojoule per kg. The heat capacity of the feed and the apple juice concentrate are 3.9 kilojoule per kg degree Celsius and 3.4 kilojoule per kg degree Celsius. The overall heat transfer coefficient is 1756 watt per meter square degree Celsius. We need to calculate what is the heat transfer area required. So I know there are a lot of numerical values here, but before we proceed with the question, can anybody tell me what is a single effect evaporator? So have you guys gone through the week's videos yet, or should I explain the tiny parts as well? Based on your response, we can modify the class accordingly. So do you guys know what a single effect evaporator is? Okay, a single effect evaporator is the kind of diagram that I showed before in the previous question. In a single effect evaporator, you will have only one unit present. We will talk about multiple effect evaporators as well, but in a single effect evaporator, you will have just one single instrument. You will have you will put the feed in, you will take the vapor and product out. You will put the steam in for heating, and you will take this condensed steam out. That is all it is. It's a very simple evaporator which is known as the single effect evaporator. There's only one unit. In a multiple effect evaporator, you will have multiple of these evaporators connected in series. That is known as a multiple effect evaporator, which we'll be discussing in the coming slides. So this is a single effect evaporator, and here it is given 132 kg per hour of apple juice is entering at a temperature of 50 degrees Celsius. So in this case, 132 is the F, or the feed F, which is given here as 132 kg per hour, and it is concentrated from 8% to 26%. So this percentage is basically the total solids that are present in the stream. So 8% is what is present in the feed, so that is equal to XF. So XF can be given as 0.08, and it is concentrated to 26%, which means when you take out the product, your total amount of solids is now 26%, which means XP is equal to 0.26. So then we already know what is the temperature. So what happens in an evaporator is you maintain a certain pressure inside the evaporator, and because of that pressure, according to the pressure that you maintain in the evaporator, the boiling point of your feed will also depend on that. Just a minute. So if you guys remember your 11th standard syllabus, the pressure is directly proportional to your temperature. Basically ideal gas law is the same concept, but pressure is directly proportional to your temperature. So if you keep a very high pressure inside your evaporator, your boiling point of the liquid will also increase. If you keep very low pressure inside the evaporator, your boiling point of the feed will also decrease. So based on the pressure, the boiling point of the feed will vary, and here it is given that the boiling point temperature is 50 degrees Celsius. So let's say that the temperature inside the evaporator, let us call it as T1. So T1 is equal to 50 degrees Celsius. I am converting it into Kelvin. So plus 273 is equal to 323 Kelvin. So when you send the feed in, you will heat it to 323 Kelvin, or if it's already entering at boiling temperature, you will just supply the steam to convert the feed into vapor and a concentrated product. So the vapor that is going out will also be at the same boiling point temperature, that is at 323 Kelvin. Hope this is clear. Whatever temperature the evaporator is in, the same temperature you will get your outlet streams, which is your vapor and your product. So here it is given as the boiling point temperature is 50 degrees Celsius, which means that the evaporator is maintained at 50 degrees Celsius in order for the evaporation to happen. So 50 degrees Celsius plus 273 equal to 323 Kelvin, which means your product and your vapor is going out at 323 Kelvin. So we know what is the latent heat of vaporization of the steam. So we are sending in steam to heat up the product. So the latent heat of vaporization of the steam is 2150 kilojoule per kg. If you remember, I said that there is generally no temperature change in the steam. There is only a phase change. So when you have a phase change, the latent heat of vaporization is what is the only thing that is differing between these two streams. So your steam is actually providing the latent heat of vaporization to the feed so that it can boil. So basically this is the energy that is being provided, 2150 kilojoule per kg. This is the latent heat of vaporization that is being provided. And then the specific enthalpy of the saturated vapor at 323 Kelvin is 2250 kilojoule per kg. So we will call the latent heat of vaporization as lambda. And here if you see the saturated vapor at 323 Kelvin, that is this stream. The V stream is coming out at 50 degrees Celsius, which is 323 Kelvin. And at that temperature, the enthalpy is 2250 kilojoule per kg. And then you have the heat capacity of the feed and the product also given here. And you have the overall heat transfer coefficient. So with these in hand, we will figure out how to calculate the heat transfer area required. So anytime when you start with an evaporator, start with the mass balance equations. So total mass balance equation, again you will not include steam in this. You have F is equal to V plus L. Inlet is equal to, or sum of inlets equal to sum of outlets. So F is equal to V plus L. And then you have mass balance of solids as well, the total solids. The same way how we solved the previous question. F into XF is equal to L into XP. There is no solid in the vapor phase, so you are not including any term from the vapor phase. So with this, we substitute the, in the last question, we discussed only two of these equations, which was mass balance equation. The moment you are asked anything regarding heat transfer, you will have a heat transfer equation as well. That is the energy balance. So when you look at energy balance here, in case of energy balance, you will consider all the streams coming in and going out, including the steam here. So when you look at the inlets, you have two inlets now. You have the feed inlet and the steam inlet. And you have three outlets. You have the steam outlet, vapor outlet, and product outlet. So each of these have some energy associated with it. And so we will balance the input inlet equal to outlet. So in energy balance, let's say S is the total amount of steam that you are letting inside the evaporator. So S is the mass flow rate of the steam. Lambda is the latent heat of vaporization of the steam. So S into lambda is the energy provided by the steam into the evaporator. This is one inlet, which is the steam. The second inlet is your feed inlet. So feed inlet, if you remember, energy associated with the steam can also be given in the form of mCp delta T. If you guys remember that equation, mCp delta T will also give you the energy associated with a with a fluid. So here in this case, instead of the mass flow rate of the feed, we have F here. F is also the mass flow rate of the feed. Cpf is the heat capacity of the feed, and Tf is the temperature in which you are sending in the feed. Temperature of the feed minus 273, which will be our reference temperature. So this will be the energy associated with the feed's inlet. So this is steam inlet, this is feed inlet. That should be equal to the sum of outlets. So in sum of outlets, you have the same liquid product concentrate coming out. So that is equal to mass m Cp delta T, that is L, which is the mass flow rate of your product stream, Cpl, which is the specific heat capacity of your product stream, and then T1 minus 273. Here the reason why it is T1 is because it will come out at the same temperature as your evaporator operating temperature. So that is T1. T1 minus 273 plus you will have the energy associated with the vapor as well, which is V into HV. V is the mass flow rate of the vapor. HV is the enthalpy associated with the vapor. So this is the energy balance that will also be uniformly applicable to across all your problems. Is this part clear? Any doubts in the energy balance? If there is any term that needs to be explained again, kindly let me know. Okay, so first we'll solve equation 2 to obtain L. We already know what is the feed flow rate of the apple, which is 132 kg per hour. We know that the stream had 8% solids, which means it is into 0.08, and we are concentrating it to 26% solids, so divided by 0.26. So 132 into 0.08 divided by 0.26 will give me L, which is the mass flow rate of the product concentrate. That comes out to be 40.615 kg per hour. Then with this we calculate what is V. Similarly, how we solved in the previous equation, we'll substitute L back inside the total mass balance equation, which is F is equal to L plus V. So from there we already know what is F, which is 132 kg per hour. We calculated L, which is 40.615 kg per hour. From there we can calculate V, which is equal to 91.384 kg per hour. So now we know we have the entire mass balance equation ready. But we need to do an energy balance as well to calculate the area required, which is asked in the question. So now I am using the energy balance and substituting whatever we know here. So we don't know what is S here. We don't know how much amount of steam we are letting in. That is not given in the question. So S into, we know the latent heat of vaporization of the steam, which is given as 2150 kilojoule per kg, and F is given as 132 kg per hour. I am converting it into kg per second. So I am dividing it by 3600. So 132 by 3600, Cpf is 3.9 kilojoule per kg, and Tf is basically the temperature at which you are sending in the feed. It was given that the feed is already at its boiling temperature, which is 323 Kelvin. So I am substituting Tf as 323 minus 273 equal to L, we found out 40.615, again converting it into kg per second. So 40.615 divided by 3600. Yeah, 40.615 divided by 3600. Cpl is 3.4 kilojoule per kg, and again T1 is the temperature at which a evaporator is getting operated, which was again 323 Kelvin. So 323 minus 273 plus V, which we calculated as 91.384, again in terms of kg per second, into enthalpy of the vapor, which is 2250. So when you solve all this, we can get the flow rate of the steam that is being sent in, which is 0.024 kg per second. Is this part clear? Any doubt in these? When you generally have an evaporator question, we first do a mass balance, then we do an energy balance. With that, we can calculate the area required. So if there is any doubt, please let me know. I'll repeat that part again. I'm proceeding as of now. So in an evaporator, as I told you, whatever heat supplied by the steam is actually the heat transferred. That is, the energy associated with the steam is being transferred to the feed for the evaporation process. So the heat transferred is equal to the energy associated with the steam, which is equal to S into lambda. So this is the amount of heat transferred. So if I calculate the amount of heat transferred, we calculated S just now, which is 0.024 kg per second. Lambda is already given in the equation, which is 2150 kilojoule per kg. From there, we can calculate what is the total amount of heat transferred, which is 51.6 kilojoules. So we know the total amount of heat transferred, and another equation of the heat transferred is Q is equal to UA delta T. So Q is the total amount of heat transferred is equal to U is the heat transfer coefficient. Basically, it will tell you how rapidly the heat transfer is happening. Higher the heat transfer coefficient, faster is the heat transfer rate. So UA is the area of the evaporator that is asked in the question. Delta T is the temperature difference between the steam and your feed and your liquid. So in this case, we already know what is Q. U is given in the question. We need to find area. We can find the delta T, which is the temperature difference between the steam and your liquid. So if I am substituting the values, Q is 51.6 kilojoules divided by the overall heat transfer coefficient is given as 1756 watt per meter square degree Celsius into delta T, which is Ts, that is temperature of steam, minus T1, which is temperature of the evaporator. So 375 minus 323, which will give me an area of 0.57 meter square. Is this part clear how to calculate the area? So after you are done with the energy balance, you calculate the total amount of heat transferred that comes from the steam, which is S into lambda. After you calculate the total amount of heat transfer, that heat is being transferred to the liquid inside the evaporator. For that, this is the equation. Q is equal to UA delta T. So you have Q, you have U, you have what is delta T. You can calculate the area of the evaporator from there. I hope this is clear. Any doubts in this? Because this particular sum has been repeated twice in the past years. So I'm not sure how the assignment, how the current assignment looks like, but this is one of a very commonly asked question, calculating the area of an evaporator. Okay, moving on to question 3. In a triple effect evaporator, the saturated steam is entering the first effect at 375 Kelvin, and the boiling point of the solution in the last effect is 315 Kelvin. The overall heat transfer coefficient for the first, second and third effects are 2950, 2100 and 1450 watt per meter square Kelvin respectively. What is the boiling point of the liquid in the first and the second effect? If the boiling point rise is negligible and heat transfer area is the same in all the effects. So before we proceed, as in the previous question, it was mentioned that it was a single effect evaporator, which means there was only one unit and you had feed steam coming in, vapor, liquid and the steam going out. That was the single effect evaporator. In a triple effect evaporator, you will have 3 different units connected in series. And one of the main part is this is to improve the efficiency, the steam economy or the efficiency of the process. So a multiple effect evaporator always has its advantages over a single effect evaporator because of something known as steam economy, which we'll be studying in the later coming problems. So one of the things that you need to notice in a multiple effect evaporator is that the moment you heat up your liquid in the first evaporator, you will have vapor going out and the concentrate coming out. So this concentrate is reheated again by the vapor itself, from the first effect itself. So you are feeding the concentrate from the first effect into the second effect, and the vapor from the first effect now acts as the steam. So you don't have multiple steams coming in, you will have only steam only in the first effect or one of the effects. Later on, any other boiling process or evaporation process will happen because of the vapor from the previous effect. So the first effect will supply energy to boil the liquid in the second effect. Again, the vapor from the second effect will provide the energy to boil the liquid in the third effect, and so on. And finally, in the last effect, you will take out the vapor to condense it and you will take out the final concentrated product. Is this part clear? What is a triple effect evaporator? So now we will figure out what is the given in the question. The given is the saturated steam is entering at the first effect at 375 Kelvin. Just a minute. Yeah, sorry. So we have what is Ts given, which is 375 Kelvin. And we know what is the boiling point of the solution in the last effect. That is, we know what is T3, which is 315 Kelvin. And for each of the evaporators, you will have different overall heat transfer coefficients. So U1 is 2950 watt per meter square Kelvin, U2 is 2100 and U3 is 1450 watt per meter square Kelvin. So we need to find out what is the boiling point of the liquid in the first and second effect. That is, we need to find out what is T1 and we need to find out what is T2. And the conditions given are that the boiling point rise is negligible and the heat transfer area is the same in all the effects. Before I proceed with the question, can anybody tell me why would there be a boiling point rise? Why do you expect to see a boiling point rise? So as and when you evaporate a liquid solution, you will have vapor going out, which means the total amount of your feed is getting concentrated more and more as you proceed with the evaporation process. So if your feed gets concentrated more and more, the viscosity will first thing is that the viscosity will increase, and second thing, because of the increase in concentration, you will have a boiling point elevation concept. If you guys remember, pure water has a lower boiling point, but water mixed with some kind of solute will have a higher boiling point. So if you guys remember the concept of boiling point elevation, so your solution will generally have a higher boiling point when compared to your pure solvent. So as and when you evaporate a feed, the total amount of the concentration of the solute will keep on increasing, because of which your boiling point will also start to rise. What boiling point you had at the initial start of the evaporation process will not be the same at the end, because now your product would have been very much concentrated and your boiling point would have drastically increased. But in this case, they are saying that we can neglect the boiling point rise. This is because often in feed we have very finely dispersed solids. Because of this finely dispersed solids, there will be a boiling point rise, but then it will be very, very small. And if you had very large suspended solids, then the boiling point rise would be very prominent. It will be significant enough, but you have a very finely dispersed particles like in the food material, your boiling point rise can actually be considered negligible. Is this part clear? We'll move on to the problem. So I'll first explain how the here, unlike the other equation, other problems, we do not know any other value. We do not know the mass flow rate of any of the steams. We do not know the temperature of any of the steams except the Ts and the T3. Okay, so the normal mass balance equations will not work out in this case, in this problem. So we'll use a different approach. I'll be showing you the derivation of this approach so that you can understand. But if you're able to remember the formula, then you can start applying it directly. So as I mentioned, the heat transfer can be explained as Q is equal to UA delta T, where U is the overall heat transfer coefficient, A is the area of the evaporator, delta T is the temperature difference between the steam and your evaporator temperature. Okay, so now when you're dealing, if you had a single effect evaporator, delta T would be straightforward, that is Ts minus T1, as we saw in the previous second question. But if you have multiple effect evaporators, in the first effect you will have Ts minus T1. In the second effect, where your vapor from the first effect will start acting as the steam. So then you'll have T1 minus T2 plus you'll have T2 minus T3, because vapor from the second effect will act as the steam in the third effect. So you'll have T2 minus T3. If you basically simplify this, you will get delta T as Ts minus T3. Is this part clear? If it was a single effect evaporator, only this will be there. If you have multiple effect evaporators, the delta T is basically a temperature of the steam minus temperature of the last effect, which is in this case, which is T3. So now if I substitute back in, if the heat transfer remains the same, if the area and heat transfer rate are assumed to be the same, in the previous equation, you can say Q, you had Q is equal to UA delta T. So I am keeping delta T in one corner and the rest I am transposing it to the other side. So we will have Q divided by U and A. So basically that can be given as Q by A into 1 by U. In this particular question, this can be given as delta T is equal to Q by A into 1 by U. 1 by U is the resistance, overall resistance. U is the overall heat transfer coefficient, 1 by U is the resistance. So you can actually add up the resistance. 1 by U is equal to 1 by U1 plus 1 by U2 plus 1 by U3. You can add the resistance in each of the effects to find the total resistance. So 1 by U can actually be split into 3 effects, that is 1 by U1 plus 1 by U2 plus 1 by U3. And when you look at the single evaporator, the first effect evaporator alone, you can say that Q by A is equal to U1 into delta T1. Is this part clear? Is it getting too confusing? Since area and the heat transfer rate are the same, I can always keep Q by A in one corner and the rest will be U1 into delta T1. This is only for the single effect, not for the entire evaporator. So Q by A is equal to U1 into delta T1. If it had been for the second evaporator, you will have Q by A equal to U2 into delta T2. Here delta T1 is this, delta T2 will be this, delta T3 will be this. That is the temperature difference in the first effect. Delta T2 will be temperature difference in the second effect. Delta T3 will be temperature difference in the third effect. So for the first effect, let's say Q by A is equal to U1 into delta T1. Since Q by A remains the same, we can substitute this here. That is U1 into delta T1 into 1 by U1 plus 1 by U2 plus 1 by U3. So again I am rearranging to find out what is delta T1. That is equal to delta T and rearranging 1 by U1 plus 1 by U2 plus 1 by U3, and you have 1 by U1 also going on this side. So basically if you rearrange, this is what you will get. Why I am doing this is because we know the entire delta T. Question has already given Ts, question has already given T3. So delta T we can calculate, but we do not know what is T1, we do not know what is T2. So we can calculate T1 and T2 if we know the overall heat transfer coefficient of each of the effects, and we know the complete temperature, the total temperature difference. This is just a derivation. You can go through this when you find time, but if you are able to remember this part also, then this is enough. So for delta T1 it is equal to delta T 1 by U1 plus divided by 1 by U1 plus 1 by U2 plus 1 by U3. Had it been for the second effect, then delta T2 is equal to delta T into 1 by U2 and then this entire denominator. That denominator will remain the same. Only in the numerator, instead of U1, you will have U2 for delta T2. For delta T3, you will have U3. So this is just the derivation for this formula. So now we know what is delta T, which is Ts minus T3. It is given in the question as Ts as 375 Kelvin. The temperature of the last effect is given as 315 Kelvin. So Ts minus T3 is 60 Kelvin. So delta T1 is equal to delta T, which is 60 Kelvin, into 1 by U1, which is 1 by 2950, divided by 1 by U1 plus 1 by U2 plus 1 by U3. That is 1 by 2950 plus 1 by 2100 plus 1 by 1450, which will give me 13.52 Kelvin. This is delta T1, this is not T1. Similarly, we will calculate delta T2. Delta T2 is again delta T, which is 60 Kelvin, into 1 by U2, which is 2100, divided by the same denominator. This is giving me a value of 18.987 Kelvin. So now when we figure out what is delta T1 is Ts minus T1. That is steam temperature or the equivalent steam. Steam temperature minus temperature of the evaporator, which is T1. And delta T2 is the steam temperature, but in the second effect you do not have a concept known as steam. It is the vapor from the first effect that is heating the liquid. So this will be T1 instead of Ts, T1 minus T2. We need to calculate what is T1 and T2. So from delta T1 and delta T2, we can calculate T1 and T2. So from this equation, delta T1 is 13.52, Ts is 375 Kelvin. From there, we can calculate T1 to be 361.48 Kelvin. And again, now that we know T1, we can calculate T2. Delta T2 is given as 18.987 Kelvin. T1 we calculated to be 361.48. So 361.48 minus 18.987 is equal to 342.49 Kelvin. The answer is option D. Is this part clear? Any doubt in the equations? This is also a sum that has been recurring for the past 2 years. Okay, this is a similar question. It's just the difference in the values. We'll solve this if we have time, but this is exactly the same sum that we solved right now. But this was the previous question was from I think 2021. This question is from 2022. So we'll solve this if we have time. As of now, we'll move on to the next question. question 5. If there's any doubt, kindly let me know. Is there anything that needs to be repeated so far? If not, we'll proceed. Okay, calculate the power required to operate the compressor of a mechanical vapor compression system for an evaporation rate of 2000 kg per hour. The enthalpy of the vapor entering the compressor is 2625.3 kJ per kg and leaving the compressor is 2711.9 kJ per kg. We need to calculate the power required. Before we start with the problem, can anybody tell me what is the purpose of a mechanical vapor compression system? Why do you require a compression system in case of an evaporator?
For the stream saturation.
For the stream what? So when you have an evaporator, you have your steam going in to heat up the evaporator and then you have the liquid coming out. And because of this heating up, you have the feed going into vapor phase and then you have a concentrated product as well. Now in order to increase the efficiency of the evaporator, instead of every time sending in fresh steam, you can actually compress the vapor that you get from the evaporator. You have a vapor phase that you get. You can compress the vapor phase and this compression results in an increased enthalpy. That is, now the vapor has a higher enthalpy once you compress the vapor. Now this compressed vapor will then be recirculated back into the evaporator after adding only a little steam. So every time you don't need to send so much amount of steam. You can just compress the vapor that you get, add in a little more of the steam, just slightly more, and then that can be used to reheat the feed that is present inside the evaporator. This is basically for both cost reduction and a more efficient process instead of sending in so much amount of steam every single time. So that is the purpose of mechanical vapor compression. So here we know heat for, in this case for mechanical vapor compression, heat transferred is equal to m into hf minus hi, where m is the mass flow rate of the vapor into hf, which is the final enthalpy after compression, minus hi, which is the initial enthalpy before the compression. So this will give me the total energy required to basically compress and increase the enthalpy of the vapor. So we already know what is the mass flow rate of the vapor, which is equal to the evaporation rate. So mass flow rate of the vapor that is coming out of the evaporator is equal to the evaporation rate, because if the evaporation rate increases, the vapor that you get will also increase. So m here is equal to 2000 kg per hour. Hi is given as 2625.3 kJ per kg. HF is given as 2711.9 kJ per kg. So if you, it's just a basic substitution. With that, I am converting kg per hour into kg per second. So I am dividing it by 3600. So 2000 divided by 3600 into HF, which is 2711.9, minus HI. I am converting kilojoules into joules. So I am multiplying it into 1000. Basically, I am bringing everything down into SI units. So with that, this is the power required, which is 48.11 kilowatts, which is option B. Is this clear?
Ma'am, it is supersaturation of steam right now.
No, nothing of that mentioned. So yeah, generally you'll get supersaturated vapor coming out. That you'll increase the pressure, compress it more, and because of that, the enthalpy associated will also increase.
Okay.
Okay, moving on to question 6. This will be a relatively easier question given that we have already discussed what is the mass balance equations. So an evaporator has a rated evaporator capacity of 242 kg per hour of water. What will be the rate of production of the concentrated juice containing 37% of the total solids from a raw juice containing 12% solids? So we already have what is the XP here, that is the total amount of solids in the product stream, which is 0.37. We know what is XF, that is the total solids present in the feed, which is 0.12. So we know what is XP and XF. But unlike the previous questions, we do not know what is the mass flow rate of the feed. What is given here is the rated evaporation capacity, which is in 242 kg per hour of water. This water corresponds to nothing but the vapor that we get after the evaporation process. So you have three streams. You have F, you have L, you have V. So 242 kg per hour of water is basically the V that is given here. That is the water that is coming out of the evaporator in the form of vapor. So total mass balance is F is equal to L plus V. And the mass balance for the solids is F into XF is equal to L into XP. So now by substituting, we'll just substitute for F, that is equal to L plus V. So L plus 242 into 0.12 is equal to L into 0.37. So we need to find out what is the rate of production of the concentrated juice, which means L is what is asked in the question. That is the mass flow rate of the concentrated juice is what is asked in the question. So if you simplify the equation further, you get 0.25 L is equal to 29.04. L comes out to be 116.16 kg per hour, which is option C. So majority of the questions you will be able to solve with just mass balance and energy balance. Sometimes you will have to solve something how we similarly solved with when we had the heat transfer coefficient of each of the effect evaporators. So we will move on to some theory based questions. Question 7. Which of the following is incorrect about a multiple effect evaporator? A. In a multiple effect evaporator, the latent heat of vapor coming out of the first effect is reused for heating the feed in the next effect. B. The steam economy is greater than that of the single effect evaporator. C. The backward feed evaporator is a single effect evaporator. And D. None of the above. Can anybody tell me which of these is a false statement? Yeah. So C is the false statement.
C.
Yeah. So the in a multiple effect evaporator, as we saw here, this is an example of a backward feed evaporator. Previously, what I showed you, the previous figure that I showed you is a forward feed evaporator, and this is a backward feed evaporator. I will discuss the difference right now. But before that, we will just go one by one with each of the statements. In a multiple effect evaporator, irrespective of whether it is a forward feed or a backward feed, the vapor from the first effect will be used for reheating the feed in the second effect. You will have steam only going in one of the effect. For the rest of the effects, it is the vapor from the previous effect that will be used for heating the fluid inside the evaporator. So A is true. And B, steam economy is greater for a multiple effect evaporator than that of a single effect evaporator. Can anybody tell me what is the steam economy?
Vapor upon stream rate.
Yeah, so total vapor that we take out at this stage, at the end of the effect, the total vapor that we take out divided by the steam is known as the steam economy. So if you are able to utilize very less steam and able to produce high amount of vapor, which means that the steam economy is good. That is, you are saving power, you are saving cost, and you are having a very efficient process. That is, by just giving very less amount of steam, you are just resupplying whatever you produce in the process itself to get the desired concentrated product. So in this case, in the case of a multiple effect evaporator, instead of giving steam at each and every effect, you are giving it on only one effect. which means the amount of steam that you're giving inside the multiple evaporator is very, very less. On the other hand, the amount of vapor that you generate is much, much more. So V by S, V is much greater than S. So the steam economy for a multiple effect evaporator is always greater than that of a single effect evaporator. And C, in case of a backward feed evaporator, is not a single effect evaporator, it is a multiple effect evaporator. So what is a backward feed is that your feed and steam will go in the opposite directions. That is, if you are putting the steam in the first effect, you will put the feed in the last effect. This is known as the backward feed evaporator. If you had a forward feed evaporator, both the feed and the steam will go in through the same effect. It's the same as parallel flow and counter flow. So in a backward feed evaporator, steam enters one of the effect. It need not be the first effect, it need not be the third effect. It can be the other way around also. You can enter the feed in the first effect and the steam in the last effect. Anything is fine, but basically your feed and steam will enter in different effects. So statement C is false. So moving on to question 8. Agitated thin film evaporator is used for dash type of fluids. A, less viscous, B, high viscous, C, medium viscous, and D, all of the above. No, the answer is not option A. So what? Before we go answer, what is the advantage of using an agitated thin film evaporator? Instead of going for a normal evaporator as we discussed before, the one of the advantage of using an agitated thin film evaporator is, as the name suggests, you have an agitator or some kind of an instrument to provide agitation or provide some kind of movement inside the evaporator. So when you have a high viscous fluid, the heat transfer coefficient will drastically drop. That is, the high viscous fluid will provide a lot of resistance to transfer the heat. It is easier to heat water than it is to heat honey or something very high viscous. It is basically because the heat transfer coefficient of a less viscous fluid is very high. Whereas for a high viscous fluid, the heat transfer coefficient is very, very low, which means the thicker or the more viscous the fluid, it is more difficult to transfer heat. So agitation actually improves the heat transfer coefficient. When you continuously stir something, it is easier to transfer heat when you are dealing with highly viscous fluids. Which is why in case of an agitated thin film evaporator, you will have an agitator in the middle which will continuously stir the fluid that is coming in. You will supply the feed in one end and take the product out in the other end, and you have a heating jacket as well where you will supply the steam. So as your feed comes in, you will continuously agitate it, and your steam that you supply will supply the heat to the feed. So because of the continuous stirring, the heat transfer will be better and you will be able to achieve a better evaporation process. For a low viscous fluid, this agitation is not necessary. The heat transfer coefficient will already be good, so the agitation is not absolutely necessary. So any evaporators that have an agitator is majorly suitable for high viscous fluids instead of a low viscous fluid. This is only to increase the heat transfer rate and the heat transfer coefficient. So answer is option B. Moving to question 9. In a falling film evaporator, the vapor and the liquid are usually separated at the dash of the tubes. A, the central annular space, B, top, C, bottom, D, both A and B. So, do you guys know what's a falling film evaporator?
Both A and B.
No, it's not the answer. The falling film evaporator, as the name suggests, you will supply the feed at the top and you let it fall as a small film as by the action of gravity. So if you look here, you'll actually supply the feed at the top somewhere here, and because of the gravity, the feed will pass through these small pipes because of the gravity by forming a small film throughout as it falls. If you supply the feed here, it will pass through these pipes by the action of gravity, and it will form a thin film as it passes from the top to the bottom. So it will pass from top to the bottom, and as it passes from top to the bottom, you are heating the outer area with the help of steam. So by the time it comes from the top to the bottom, it will reach the boiling point. It will start evaporating. You'll then direct the feed to this area, where now the feed is at its boiling point temperature. So you will collect your here you will have the boiling point temperature of the feed. So liquid all will be collected here, whereas vapor is now allowed to pass through this area, and that vapor you can collect separately. I am repeating again, the feed will fall through from the top to the bottom. By the time it falls, it will get heated up by the steam. By the time it reaches the bottom of the evaporator, it will already be at its boiling point. So whatever concentrated liquid that you get, you can collect it at the bottom, and the vapor that is now free to move will pass through this area, and this can be collected separately. So any separation that happens at the bottom, because since it's a falling film evaporator, you are supplying the feed at the top and you are letting it to fall by the help of gravity, which is why the collection happens at the bottom. So the answer is option C. Okay, question 10. In a multiple effect evaporator, the pressure in each succeeding effect is dash, so that the boiling point of the liquid is dash in each effect. So lowered, the pressure is lowered, so the boiling point is increased. B, the pressure is increased, so the boiling point is increased. C, the pressure is lowered, so the boiling point is lowered. And D, the pressure is increased, so that boiling point is lowered. The answer is not B. Think again. In a multiple effect evaporator, you are sending the vapor of the first effect into the other effect, the subsequent effect. So let us say this, so in the first effect you have the steam that is helping it to evaporate. From the second effect onwards, it is the vapor from the previous steam that is helping it to evaporate. Now will the vapor temperature be the same as the steam temperature? Yeah, the answer is C. Will the vapor temperature be the same as the steam temperature? Let's say I am giving steam here, and there's process and evaporation, and you have vapor here. This temperature and this temperature will obviously not be the same. Had it been the same, you will have no heat transfer at all. If you remember, Q is equal to UA into delta T. The delta T is steam minus T1. And your vapor temperature is also T1. So unless and until you have this difference, you will have no heat transfer. So always in the first effect, the steam temperature Ts will always be greater than T1, which is the temperature of your vapor. I hope this part is clear. So now since the vapor now has a lower temperature, it will not be able to heat it as effectively as the steam. If you provided steam, it will be very easy to evaporate this fluid. But you are not providing steam in order to cut down on cost and increase the efficiency. You are providing vapor instead. This vapor has a slightly lower temperature, which means now it will be very difficult to evaporate, to transfer the heat and evaporate. So in order to reduce the difficulty, what we do is we maintain the pressure of the next effect slightly lower. if we maintain the pressure of the next effect slightly lower, the boiling point will also be lowered. As I mentioned in the one of the earlier slides, the pressure of the evaporator will dictate the boiling point of your fluid. Lower the pressure, lower the boiling point. Higher the pressure, higher the boiling point. So if you maintain a low pressure, you will have a very low boiling point in the second effect, and now your vapor can easily boil the liquid here. Since this vapor has lesser energy than that of the steam, you can lower the boiling point here so that this less energy vapor can itself result in evaporation. So similarly again, the vapor that is coming here will have even lesser energy than this vapor. So now that this has even lesser energy, we'll make sure that the pressure in this effect is even more lower than P2. So that the boiling point is even lesser and you are able to cause evaporation much more easier. So what I'm trying to say is P1 is always greater than P2, P2 is always greater than P3. This will help the vapor to evaporate the liquid in the evaporator. So in a multiple effect evaporator, the pressure in each succeeding effect is lowered so that the boiling point of the liquid is also lowered in each of the effect. Hence, there is a temperature difference created for the vapor from one effect to condense in the next effect and boil the liquid in the form of vapor. This is all because your vapor is not as efficient as the steam. So you need to lower the boiling point in the next effect so that whatever energy this vapor has, that is enough. So I hope this is clear why the pressure is lowered at each of the effect. In case you want me to repeat, kindly let me know. So the answer is option C. The pressure is lowered in multiple effects so that the boiling point is also lowered. So this is applicable for both a forward feed multiple effect evaporator and a reverse feed. So irrespective of where you are sending in the feed and where you are sending in the steam, P1 is always greater than P2, P2 is always greater than P3. Okay, moving on to question 11. What are the factors affecting evaporation? A. Pressure and temperature. B. Solubility. C. Concentration. D. All of the above. So we'll discuss each factor one by one. So first thing, solubility. So as you keep on evaporating, the concentration of your solution will keep on increasing, and the max solubility is the maximum concentration of the solute that can be dissolved in the solution. So the maximum concentration of the solution obtained by evaporation depends on the solubility of the solute. So let's say you can dissolve a solute only 100 mg per liter. So if you try to evaporate more of the liquid, your solute will start precipitating out, and you don't want that. You still want your solute to be present in the liquid only. So based on the solubility of the feed, you have to determine how much you want to evaporate and how much you don't want to. If the solubility is very less, you can evaporate only less. If the solubility is much higher, then you can evaporate lots of water and still have the solute in the solution form. So the solubility does affect the evaporation process. Next is pressure and temperature. So the boiling point of the solution is dependent on the operating pressure of the system. So as I mentioned, higher the operating pressure of the evaporator, higher is the boiling point temperature. So if you have a high pressure maintained inside the evaporator, you will have to supply a lot of steam to reach the boiling point and then result in evaporation process. So the pressure and pressure we maintain inside the evaporator will directly influence the temperature of boiling, and that will again affect the evaporation rate. See, concentration. As the evaporation proceeds, the solution becomes more and more concentrated. Again, it will become more viscous, This will result in the heat transfer coefficient to drop. As I mentioned before, the more thicker solution you have, it is more difficult for the heat transfer to happen, and this is because your heat transfer coefficient starts reducing with viscosity, with increase in viscosity. So all of these factors affect the evaporation process. Hence the answer is option D. I hope this is clear. Any doubts? Okay, question 12. We have two statements. We have to figure out which one of these is true or false. So statement 1, reducing the operating pressure decreases delta T. Statement 2, preheating the feed can reduce the area of heat transfer and thus the size of the evaporator. So which of these are true and which of these are false? So does reducing the operating pressure decrease the delta T? Yeah, statement 1 is false, because reducing the pressure will not reduce delta T. It will reduce the boiling point or the operating temperature of the evaporator. There is a difference. So reducing the operating pressure will reduce T1, but delta T is equal to Ts minus T1. So if you reduce T1 and you fix the Ts value, so if you keep reducing T1 value, the delta T will actually increase. It is the T1 that decreases with decrease in pressure. Delta T will actually increase. So statement 1 is false. I hope this is clear. Do not get confused between what is delta T and what is T1. Okay, it is operating temperature that reduces, but the difference in temperature actually increases. Statement 2, preheating the feed can reduce the area of the heat transfer and thus the size of the evaporator. Is this true or false? Yeah, the second statement is true. The why we preheat the feed is because if you preheat the feed before sending it into the evaporator, the feed is already heated up, which means you would now require less heat transfer to enable the evaporation process. So instead of sending the feed at 50 degrees Celsius, if you already send it at 75 degrees Celsius or 80 degrees Celsius, the amount of heat that you need to supply is actually on the lower side, which means you can afford to lower the area of the heat transfer and still get the desired evaporation efficiency. So the cost of the evaporator also goes down if you are able to reduce the size of the evaporator, which is why often people prefer to preheat the feed. And this preheating of the feed can be done by the vapor from another process. Like say if you started the evaporation process and you have the vapor coming out, that vapor can actually be used to, you have that mechanical vapor recompression process and all. So that vapor can actually be used to start heating up the feed before it starts coming inside the evaporator. So that way you can reduce down the cost of the evaporator, you can reduce down the amount of heat transfer required. So statement 2 is true. Answer is option B. Moving to question 13. The straight lines obtained between the boiling point of a pure solvent and boiling point of a solution for different concentrations of a solute is called A. During lines, B. Fourier lines, C. Isobars, and D. Boiling point elevation. It's not D. D is the phenomena that happens. When you increase the concentration of the solute, boiling point elevation happens. That's the phenomena. That is not the name of the lines. Question asked is what is the name of the straight line that you obtain if you plot the boiling point of the solvent in one axis and the boiling point of the solution in the other axis. the name of the plot is known as the During plot. So in a During plot, you have boiling point of the pure solvent in the x-axis, you have boiling point of the solution in the y-axis, and you have multiple lines. These are generally straight lines because the boiling point of the solution is directly proportional to the boiling point of the water. So Tb is equal to some proportionality constant into Tb of water. So you will get, when you plot Tb of solution versus Tb of water, you will get multiple straight lines. These straight lines will vary with different concentrations. So 0% concentration will have a line, 5% concentration will have another line, 10, 15 will have different lines. So each of these lines is known as the During lines, and this entire plot is known as a During plot. The answer is option A. The concept is the boiling point elevation, that's the concept, but the name of the lines and the plot is known as the During plot and During lines. Okay, moving to question 14. Which of the following evaporators are used for highly viscous food product like tomato puree? A. Climbing film evaporator, B. Falling film evaporator, C. Jacketed open kettle evaporator, and D. Plate type evaporator. Now in a falling film evaporator, if you have a highly viscous, as I mentioned in the previous thing, the moment you are dealing with high viscous food product, you require an agitator. In this case, I have not mentioned that it is an agitated falling film evaporator. It's just a normal falling film evaporator. So you need to first understand, unless and until it is mentioned, do not assume that it is an agitated film evaporator. I know there was a question that mentioned about falling film evaporator used for highly viscous food product, but there it was specifically mentioned that it was an agitated evaporator. But generally, falling film evaporators are also possible without an agitator. Whereas in case of a jacketed open kettle evaporator, this is how it looks. You have an open kettle or an open bowl like structure. You will have a jacket here at the bottom that will supply the steam for the heat transfer. And inside this bowl or the kettle, open kettle, you will have an agitator or a stirring system. This will be connected to a motor to stir the fluid present inside the evaporator. So generally for highly viscous fluids, you will need an evaporator with an agitator, and unless and until mentioned, jacketed open kettle evaporator is an example where an agitator is installed. So the answer is option C. Generally in a falling film evaporator, you do not have an agitator, you just make it pass through by the action of gravity. Very rarely, unless and until mentioned, you will have an agitator attached to it. And the same goes for the rest. In case of a climbing film evaporator, you will pass the feed at the bottom and you will let it climb up the evaporator with the help of pumps and stuff. Okay, question 15. Okay. In a single effect evaporator, this is a numerical, this is a slightly bigger numerical. So in a single effect evaporator, the boiling film coefficient inside the tube is 1500 watt per meter square Kelvin. The steam condensation film outside the tube is 7000 watt per meter square Kelvin. There are a total of 20 vertical tubes, 18 millimeter and 20 millimeter inside and outside diameter respectively, of 5 meter length, and are used and a 15 degrees Celsius temperature difference is maintained across the tube walls. The thermal conductivity is 15 watt per meter Kelvin. The latent heat of vaporization of water is 2350 kilojoule per kg. Assume no boiling point rise, no heat loss, and the feed enters the evaporator at the boiling point. Calculate the steam requirement in kg per hour. So the moment you ask steam requirement, it is asked about S. If you remember the second question, we had S as the mass flow rate of the steam. So that is what is asked in the question. But this is slightly different. We do not have any feed or any values. We just have the heat transfer coefficient at each and every stage. So this is a slightly different question that we'll be discussing. So for any heat transfer process, the heat transfer flux, that is small q, is directly proportional to the temperature difference and inversely proportional to the resistance, which means that higher the temperature gradient, faster will be or higher will be the heat transfer flux, or lower the resistance, higher the heat transfer flux. Delta T is the temperature difference, capital R is the resistance for this heat transfer. So lower the resistance, higher the heat transfer. So for any heat transfer process, small q is directly proportional to delta T by R. So in a convection process, if you look in the convection process, small q is equal to H into delta T. And as I said, small q here is flux. Flux basically means total heat transfer divided by area. The moment you have any term called flux, it is divided by area. So small q is equal to capital Q, which is the total heat transfer divided by area. And the same thing I am writing as delta T divided by 1 by H. So if you compare this equation with this equation, you can see that the resistance is equal to 1 by H. So in a convection process always, resistance is equal to 1 by H. Here H is the heat transfer coefficient that is mentioned here. The heat transfer coefficient mentioned here is 1500 watt per meter square Kelvin, and on the other side you have 7000 watt per meter square Kelvin. So all these are heat transfer coefficient. So the resistance for a convection process is 1 by H. For conduction process, Q is equal to K into delta T by X. This is the equation. So Q is equal to delta T X by K. Here X is the thickness of the solid substance through which it is conducting the heat, and K is the thermal conductivity. So if you compare this equation and this equation, the X by K is the resistance and X is the thickness of your solid substance through which the heat is transferring. So with this basics, 1 by H as the resistance for convection and X by K as the resistance for conduction, it is now mentioned that what happens in an evaporator is that you have steam on the outside of the tube, you have your food passing in the inside of the tube. The heat has to transfer from the bulk steam onto the surface of the tube, outer surface of the tube, and then via conduction it has to pass from the outer surface of the tube to the inner surface of the tube, and then again via convection the heat has to transfer from the inner surface of the tube to the bulk of the liquid. Is this clear? So there are three different processes involved. First, heat has to transfer from the steam to the outer surface. That will have a certain resistance due to the outer film that is forming. So as heat touches the tube, it will start condensing on the surface of the tube. So that will form an outer film like layer that will cause some resistance, heat transfer resistance. Then there will be resistance due to the conduction, that is the heat has to transfer from the outside of the tube to the inside of the tube. So there will be resistance due to conduction. Then again there will be a film forming at the inside of the tube as well due to the feed evaporation. So there will be resistance due to the inner film. So the total resistance, you can always add up the resistance. The total resistance is equal to resistance due to the outer film plus resistance due to conduction plus resistance due to inner film. So if I consider again for the total heat transfer, instead of separately considering for heat conduction and convection, let's say here in this case Q is the total heat transfer, that is equal to U into delta T. In this case U is the overall heat transfer coefficient that includes all these three processes. Where U is the overall heat transfer coefficient that includes all the thermal processes. So the total resistance here, again if I consider Q is equal to delta T divided by 1 by U, then the total resistance is 1 by U. So basically if I plug it back into this equation, 1 by U is equal to 1 by HO, that is the heat transfer coefficient at the outside film, plus X by K, which is due to resistance due to conduction, and resistance due to inner film is 1 by HI, which is due to inner film. So, and the thickness of the tube can be calculated as the outer diameter minus inner diameter, which is 0.02 meter minus 0.018 meter, because this thing is already given here, 18 millimeter and 20 millimeter. So when you subtract it, that is the thickness that it has to travel, which is 0.02 minus 0.018, that gives 0.002 meters. That is your thickness. So we already have in the problem what is HO is given, X is now something that we calculated, K is given, and HI is given in the equation in the problem. So I'm just substituting the values. If you guys remember the problem, the inside the boiling film inside the tube is given as 1500. This is HI. HO is given as 7000. K is given as 15 watt per meter Kelvin. So if I substitute the values, I get 1 by U is equal to 1 by 7000 plus 0.002 divided by 15 plus 1 by 1500. So U comes out to be, from there I can calculate the overall heat transfer coefficient, which is U, that is equal to 1060.6 watt per meter square Kelvin. So for this equation I have what is U. Delta T, which is the total temperature difference, is already given in the problem. So that is equal to small q, which is the heat flux. If you remember, heat flux is equal to the total heat transfer divided by area. So first we'll calculate what is the area of heat transfer. So the area of the heat transfer is the curved surface area. So you have hot fluid here, you have cold fluid here. The heat transfer happens through the curved surface area of the pipe. So that is the heat transfer area, which is 2 pi R naught into L. So if I substitute the values, this 2 pi R naught is 20 millimeter, D naught is 20 millimeter, so R naught is 10 millimeter. So 0.01 into so the length is given as 5 meters, so into 5, and you have a total of 20 vertical tubes. So you need to multiply the number of the tubes in order to get the total surface area of heat transfer. So 2 pi R naught into L into total number of tubes. So that will give me the total area of heat transfer, which comes out to be 6.283 meters square. So again, if you remember, the heat transfer, total heat transfer is equal to the heat transferred by the steam or the hot fluid, which is equal to S into lambda. That is equal to UA into delta T. Notice the difference between small q and capital Q. Small q is equal to capital Q divided by A. So given that, I am just substituting the values. We do not know what is S. S is what is asked in the question. So S into 2350 kilojoule per kg. I am converting kilojoules into joules, so I am multiplying into 1000. So 2350 into 1000 is equal to U, which we calculated as 1060.6, area which we calculated as 6.283 meters square, and delta T, which is already given in the question as 15. From there I can calculate what is S, which is 0.0425 kg per second, which is equal to 153.15 kg per hour. The answer is option D. Is this part clear? Any doubt in the sum? We calculate what is the total heat transfer coefficient from the individual processes. Outside convection plus conduction plus inside convection. From these resistances, you can calculate what is U. You can calculate what is the area of heat transfer. So you know UA, delta T is already given in the question, and lambda is also given in the question. From there you can calculate what is S or the steam requirement. Hope this is clear. Okay, question 16. Again, in a This is very similar to one of the problems that we solved. This is the same problem that we solved for calculating the heat transfer area. We'll solve this later because this is exactly the same problem that we solved in the second question. We'll solve the rest of the problems, and if we have time, we'll get back to the same problem again. Okay, in a single effect evaporator, 0.5 kg per second feed entering at a boiling point temperature of 55 degrees Celsius is concentrated from 15% to 45%. So you have F here, you have XF, you have XP. Saturated steam is entering at 375 Kelvin, which means TS is also given here. The latent heat of vaporization at 375 Kelvin is 2050 kJ per kg, which means lambda is given here. The latent heat of vaporization is lambda is given here. The specific enthalpy of the saturated vapor at 328 Kelvin is given as 2250 kJ per kg. So specific enthalpy of saturated vapor means HV, that is the enthalpy of the vapor that comes out after evaporation. The heat capacity of the feed and the concentrated steam, that is CPF, is 3.2 kJ per kg degree Celsius, and Cp of L is 3 kJ per kg degree Celsius. The overall heat transfer coefficient is 1550 watt per meter square degree Celsius. We need to calculate the steam economy. And when we mean by steam economy, it is V by S. So we first need to calculate what is the flow rate of V, and then we need to calculate what is S. From there we can calculate the steam economy. So again, I have all the given here. F is given, T1 is given, that is 55 degree. Since the the vapor is going out at 328 Kelvin, that the vapor temperature is always equal to T1. So T1 is also 328 Kelvin. XF is 0.15, XP is 0.45, lambda is 2050, HV is 2250, CPF and CPL are 3.2 and 3 kJ per kg, and U is 1550 watt per meter square Kelvin. So we'll start with usual mass balance. So total mass balance is equal to F is equal to V plus L, and the mass balance of the suspended solids is F into XF is equal to L into XP. So, and the energy balance again is S into lambda, which is the energy of the steam coming in, FCP into delta T, that is FCPF into TF minus 273, that is the energy associated with the feed stream, is equal to LCPL T1 minus 273, which is the energy associated with the concentrated product, plus V into HV, which is the energy associated with the vapor that is coming out. So this is the total energy balance. So we can calculate V from the mass balance, we can calculate S from the energy balance. So first we calculate L. Since we know what is F, XF and XP, we can calculate L. So F is 0.5 kg per second, XF is 0.15 and XP is 0.45. So you get L as 0.16 kg per second. From L, we can again calculate V from the total mass balance equation. That is F minus L will give you V. So 0.5 minus 0.166 kg per second will give me V, which is 0.33 kg per second. Hope this is clear. Always calculate V and L from the mass balance equations if the given the other parameters are given. S is something that you can always get from energy balance. So I am now plugging in the values into energy balance. So S into 2150 plus 0.5 kg per second into CPF, which is 3.2, and TF, the feed is already entering at the boiling point, which is 323 Kelvin minus 273, equal to L, which we calculated as 0.16 into CPL, which is 3 kJ per kg, and T1 is 323 and then minus 273 as the reference temperature, plus V, which is 0.33, and HV given as 2250. So I am just plugging in the values inside the energy balance. From there you can get S is equal to 0.3359 kg per second. So we know what is V, we know what is S. from there we can calculate the steam economy, which is V by S, which comes out to be 0.99. The answer is option D. These PPTs will be made available to you immediately tonight itself. You can go through the PPT. The videos will be uploaded pretty soon, so that in case of any doubts you can refer back to the recorded sessions. So moving on to the last question. This is a true or false question. Statement 1. Scraped surface evaporators are mainly used for low viscous foods. And statement 2. In an agitated film evaporator, agitator is provided to increase the heat transfer coefficient. So which of these statements are true? So you will get a hint from the name of the evaporator itself. In a scraped surface evaporator, it is used for low viscous food. Is it true or false? Yeah, the answer is option A. So in case of a scraped surface evaporator, you will have continuous scraping of the surface. That is, when you deal with high viscous foods, it will often stick to the walls. In order to prevent the sticking of the walls, you will have an agitator or some kind of a scraping mechanism that will constantly scrape off all these crystals that are sticking onto the walls. So the viscous foods or foods that require crystallization often stick to the walls, especially when you start evaporating. So the more and more you evaporate, the more viscous it becomes, the more concentrated it becomes, and you will have a lot of food sticking onto the walls, and hence it requires scraping.
I use scrap.
Sorry? Okay, hence the scraped surface evaporators are used for high viscous fluids. For low viscous fluids, the chances of it sticking onto the walls is not that high. So you do not require a scraping mechanism at all. So scraped surface evaporators are mainly used for high viscous food. So statement 1 is false. So in this case, as you can see in the diagram, you have scraper blades that will continuously scrape out any food particles that are sticking onto the walls. And statement 2, as I mentioned, in an agitated film evaporator, the agitator is provided to constantly stir the fluid and increase the heat transfer coefficient. And the heat transfer coefficient, and this is absolutely necessary because as there is a water content lost during evaporation, it results in an increase in viscosity. And the more increase in viscosity, the more difficult it is to transfer heat. So you continuously need to stir it in order to increase the heat transfer coefficient. Hence statement 2 is true. The answer is option A. So with this we wind up today's class. I didn't discuss two of the problems because it is exactly similar to the problem that we already discussed. Only thing is that the values are changing. But in case if you still because of lack of time, I'm not discussing those problems, but in case you guys have any doubts in those problems, you can get back to me. I'll discuss those problems as well.